Good afternoon, Prof. Sorry.
Sorry,
muted.
I was muted, yeah.
Good afternoon.
Can you hear me well?
Yeah, absolutely. It's good to
Very
have
good.
you. Yeah.
Very good. Very good.
Do you want to share your screen now?
Yes, give me a second.
And then we'll try the setup. Yeah.
Can you see my screen now well?
Yes, we see your screen. Yes.
Okay, very good. So I think
Could
we
you
are
advance?
all...
Could you advance it once so that you see the moves forward?
Yeah. Okay.
Yeah. Okay. Yeah. Perfect.
So I think we are good.
Yes, sir. Yeah.
And whenever there are probably still a few minutes, 10 minutes, people assemble slowly usually. So we'll give some time to everyone to get in. And after that, pretty much whenever you start, we will start.
Okay. Okay. Thank you very much. Yeah. So probably start at 5 past the hour.
Yeah, I think this is usually good time. At
Yeah,
the time,
thank
most
you.
people who want to join will be already online.
Yeah. Thanks.
So, close it for now.
Oh, yeah, good afternoon, everybody, or good everybody. We'll be starting shortly. Prof is here. Actually, so in like 7-8 minutes, we'll be starting. But before Prof starts, let me do a quick advertisement. So in December, we'll be having the 12th International Conference of the African Material Research Society, AMRS. So some of you already know about AMRS. AMRS happened in the conference. The last one happened in 2022. It's a biennial conference. We have it every 2 years. So the last one was in Senegal in December 2022. And the next one will be in Rwanda. Okay, so let me show you a slide, but then we'll come back to Prof's slide after this. So this is our slide for the conference. It will be happening in Rwanda, 16 to 19 December 2022, the African Material Research Society Conference. So it's the 12th International Conference. It will be happening in Rwanda at the Kigali Convention Center. Okay. Actually, we expect 2 Nobel laureates, Professor Francis Arnold, who got a Nobel Prize for development of enzymes using an evolutionary method. And also we'll be having Professor Novoselov, who discovered graphene. Yeah, so we expect both of them to be there. The abstract submission actually closed yesterday, but we plan to extend it. So you can still go online to try to submit your poster. So we'll be happy to have you at the conference. Actually, Professor Yury Gogotsi will also be one of the plenary speakers at this conference in December. Okay, so I hope you can attend, and you can, let me see where the website is. Yeah, so if you go to africanmrs.net/Rwanda-2024, details are there. For students, there's an early career program. Sorry, there's a pre-conference for students and early career researchers, and that is 14th to 15th of December. So 2 days before the conference, at Kigali also, then we'll have this pre-conference. If you go on the website, there are many things about the conference, about the pre-conference that are quite interesting. So I will encourage you, you'll learn about electrospinning, you learn about how to use SEM, because there's a company that will be bringing their tabletop SEM, Thermo Fisher Scientific, and we're training people on how to use SEM. So those are some of the things that will be happening there. Okay. So thank you. Let me stop sharing.
Yeah, I look forward to speaking at this conference as well and visiting Kigali in December.
Thank you very much, Prof. I actually look forward to meeting you in person there. Yeah.
Looking
So
for
we can have
tickets
coffee
now.
together.
Mhm.
Yeah, so that we can have coffee together. Actually, Rwanda has a very good coffee.
Excellent here.
Yeah.
You see, like I live on coffee.
Oh,
And I
yeah.
see Bala is here as well.
Oh, okay, that's great. Yeah. Okay.
Hello, guys.
Yeah.
Omolulu.
Yeah. Hi, Prof Bala. Hi. Yeah. So Prof Bala is
I'm
the
good.
president of the AMRS. Yeah. So he's the president of African Material Research Society, Prof Bala. Yeah. So in like 3-4 minutes, we'll start so that everyone joins us. And then, yeah.
Okay, that's good.
Yeah. I think Bala should say a few words. Yeah.
Yury,
You should
it's
say a
good
few
to
words
see
to
you
everybody.
again.
Yeah.
What?
I'm saying Yury.
Mhm.
Can you hear me?
Yes, Bala, I hear you.
Yeah, good to hear and nice to see you again.
Look, it's great to see you again, not in person this time, but I look forward
Yeah,
to seeing you in Kigali, if not before that at some conference.
yes, indeed. Yeah, and thank you very much for accepting to give this colloquium for our African researchers and globally. And I'm happy that I had so now have been defending her pre-doctoral yesterday. And congratulations once again for that. Yeah.
Yes.
Yeah.
We are hosting now 3 people from your group at Drexel who are here for the conference. Mati, Patu, and Sokna, of course.
Yeah, exactly. Okay. So, as you said, we see you in Rwanda.
Yeah, looking forward to it.
Thank you very much.
Okay. It's probably time to share the screen for me that we are ready.
Prof, do you want to take questions at the end or during the talk?
Yes, absolutely. And people can both ask questions online using meeting chat or just raise a hand and ask questions verbally. Whatever is preferred, and I will try to answer as many questions as I can.
Okay, thank you very much. Okay, let me see. Okay, so good afternoon, everybody. We are happy to have Professor Yury Gogotsi give us a colloquium today. So this is a colloquium series that we've been having for the African Material Research Society. So today we have an important speaker, Professor Yury Gogotsi. He's a distinguished university professor and Charles T. and Ruth M. Bach Endowed Chair in the Department of Material Science and Engineering at Drexel University in Philadelphia, US. He's the founding director of the A.J. Drexel Nanomaterials Institute. Together with his students and colleagues, he made principal contributions to the development of materials for electrochemical energy storage and discovered MXenes. He's recognized as a highly cited researcher in material science and chemistry and a citations laureate in physics by Clarivate Analytics. Prof. Gogotsi has received more than 60 awards for his research and teaching activities, including the Ceramic Prize from the World Academy of Ceramics, the AMRS Medal, the Jan Czochralski Award from from AMRS, the European Material Research Society, the ACS Award in the Chemistry of Materials, and so on. Prof. Gogotsi is a fellow of the National Academy of Inventors, the World Academy of Ceramics, the European Academy of Sciences, Academia Europea, and many professional societies. And he also hosts honorary doctorates from several European universities. Today, Professor Gogotsi will be talking to us about 2D carbides and nitrides for advanced technology. Thank you very much. So over to you, Prof.
Amol, thank you very much for this kind introduction. Thanks to you and Professor Bala, the president of the society, for inviting me to speak. What I will do today, I will try to explain you this large family of two-dimensional materials, carbides, nitrides, of transition metals, which we call MXenes, where M stands for a metal like titanium, niobium, vanadium. X stands for carbon or nitrogen, and the suffix "in" shows their two-dimensionality, just like a graphene or silicene, germanium. It shows that these materials are just a couple of atoms thin. So red dots here are transition metals, black dots connecting them, carbons, nitrogen. They come in a variety of colors. It means optical properties, electronic properties. You may notice complementing color, for example, green in a film reflection, red in transmission. They have unique optical and electronic properties. They also come in a variety of structures that you can see on schematic on the cover of our book. And what is important, they are relatively easy to make. So what it means that you don't need to have $1 million worth of equipment to make and study those materials. So they may find many practical applications. And I will talk about some of those applications after describing materials to them. But before I start, I wanted to mention that all the work I show to you is done by researchers in my group, which is always very, very international. And there are always students also coming from Africa. For example, Sokhna Ding from Senegal. And we have a student, had student from Tunis, Morocco. A student from Egypt was the first one who discovered MXenes, Michael Naguib. And just now, we host, in addition to Sokhna, two other former visitors, postdoctoral researchers, Mati, Fatou, and they both are originally from Senegal. And you see this picture was taken yesterday, July 31st, here when Sokhna delivered this talk. So again, we're international. We work together to solve problems that you may raise here. We actually buy precursors from Ukrainian company. We collaborate with many people around the world, particularly in South Africa with Ncholo Manyala. We published a number of papers together and hosted him earlier this year. But of course, many, many others. Just because no one can solve all the problems alone, new materials require solutions that can be offered by many different people. And since this is a materials research society group, I don't think I need to talk much about the role of materials in progress of humanity. But one thing is important. People moved to a different era of development, from stone to bronze, iron age, and our modern age of silicon-based electronic semiconductors. The new materials with principally different properties appeared, much better than the previous one. One with metal tools could do things that one cannot do with stone tools. And it doesn't mean that we don't use stones anymore. We build using stones, but we can do other things, not only like a metal tools using machinery, but we can create computers. And in the future, what we believe will happen, we will move to a different era because of availability of nanomaterials. Materials that instead of taking a piece of metal or stone or a silicon ingot and carving something out of it, like taking silicon ingot, slicing, dicing, and after that etching out something. We will assemble materials from two-dimensional and other low-dimensional building blocks like bricks or Lego stones, but atomistically thin, few nanometers thin at maximum, 1 to several layers of atoms. So this will open totally new opportunities. And materials are important in solving a variety of problems in the world here. From energy to water to healthcare and many, many others. And if we solve all these problems that I marked with asterisks here, we will be able to solve other problems, including poverty and many, many others. In particular, one of the problems we work in my group, we work a lot on energy, energy harvesting, energy storage, generation, from batteries, supercapacitors to electrocatalysis, hydrogen. And this is again where we use nanomaterials, because we cannot solve problem of harvesting, storage energy, hydrogen generation, storage without nanomaterials. But nanomaterials is a very, very broad field. Actually, you take charcoal, activated charcoal, or activated carbon, we'll call it here. This is a nanomaterial. It has nanoscale porosity. But different materials have different capabilities. And you may or may not know much about MXenes, but I'm sure you have all heard about graphene. You have just heard that Professor Kostya Novoselov, who together with Andre Geim discovered new physics in graphene in 2004, will be speaking at the African AMRS meeting in Kigali in December. This discovery actually opened eyes to scientists that there are many other materials that are similarly very thin, like molybdisulfide, boron nitride, clays even, oxides, clays, they are two-dimensional materials, few atoms thin. And when separated in these layers, they can have different properties. But moreover, scientists realize that even materials that don't have layered precursors, like antimony, phosphorus, they still can, silicon, they can still be made in two-dimensional sheets by various chemical routes. And in 2011, we discovered carbides, nitrides, which actually very different from other materials, because majority of two-dimensional materials are dielectrics, semiconducting. Some of them are semi-metals or poor metals. Graphene, for example, is not really a metal. It's zero-dimensional semiconductors. It has no free electrons carriers. You need to create defects or dope it to create carriers. MXenes, like titanium carbide, I will mainly talk about this material, first discovered, most common, easy to make, is a true metal with a high density of state at the Fermi level, high concentration electrons, like a two-dimensional clay particles. So what we believe that in the future, we will build materials assembling from solution, from a vial, in a simple, inexpensive way, various two-dimensional flakes to create materials with unique properties. And I will try to show you today how one can make super strong materials, stronger than steel, materials with very high conductivity like metal at room temperature, just by piling up and properly assembling two-dimensional flakes. Now, to introduce MXenes, it's also important to mention, we can make them using a variety of different metals. Lanthanides can substitute on M side in a MXene. We can use carbon, nitrogen, oxygen can substitute for them. But also, you definitely know from your high school chemistry courses that metals exposed to environment like water, air, will never stay non-terminated. They will pick various moieties, whatever, oxygen, chlorine, hydrogen from the environment. So on the surface, we mark it as a T group, X because different can be and mixed ones. They can have halogens, oxygen, hydroxyl groups. They can have chalcogens, amino groups, phosphorus, antimony. We predicted arsenic can also be formed, just need to be experimentally demonstrated. So if you just take 4 basic structures with 2 to 5 layers of transition metals, dozen of transition metals, carbon, nitrogen, carbide, or nitrides, you will end up with close to 100 of possible combinations. Take another dozen of surface terminations, you end up with about 1,000 of possible combinations. Not all of them may be thermodynamically stable, but there are actually many others which I'm not showing here. So we can have at least 100 of new materials, 1,000 new materials that can be created, stoichiometric materials. But we can also mix and match different materials, elements, making infinity of new materials. The first one discovered was titanium 3C2 with oxygen OH fluorine terminations in 2011. And it was actually discovered by a student from Egypt, from Africa, Michael Naguib, working with Professor Barzoum and myself at Drexel University. By now, decade after, we have about 50 Mn+1Xn stoichiometric compounds. And again, multiply by many surface terminations. About 50 of solid solution, and different elements are mixed. And an infinite number more can be built, created in laboratories. So we can have simple MXenes. It's like a slice of sodium chloride lattice of conventional cubic carbide. We can have atomic sandwiches, where one metal is on the surface, for example, moly or chromium, another, like titanium, is in the middle. We can make materials with alternating atomic columns of element, or etch away one of them, and have like a trenches, atomically thin trenches on the surface, vacancy trenches. And of course, we can put different functional groups on the surface, which will determine to a very large extent the surface chemistry. So basically, we learn how to atomistically design new materials, not take from nature what is given, but mix it and chemically in a vial make new materials. And we can mix and match M element, X element, and making solid solution. Actually, up to 7 different elements in high entropy multi-elemental MXene, where we can mix different metals. So sky is the limit really for discovery of new materials. And nowadays, people also make borides, silicide, carbochalcogenides, variety of materials in 2-dimensional sheets with different properties. And research is, of course, is going on worldwide. You can see that US and China are leading, but there are many African countries from which papers on MXenes already have been published, and these data are already dated, so about a year old. So I'm sure there are probably more now. And this is from Web of Science, which also doesn't cover necessarily everything. But the bottom line is that there are many people around the world working on MXenes. There are many papers, there are many patents. If you want to learn about MXenes, a good starting point is this special issue of CNN News, this American Chemical Society journal, which has a nice popular cover story about MXenes. It is a March 25th issue from this year. So if you want to get a nice, easy to read overview, look at this paper. And what you will also see that United States, where we discovered MXene, is not dominating number of publications. China captured the lead. But for example, India, where very little was done recently, is now producing 8% of world publication. Korea, Europe, African countries are still within this 5% of other countries, but I hope that there will be fast development. As you see on example of India, within several years, India became a major force in research on MXenes. Now, how we make MXenes? We usually start with layered ceramics, which are produced by conventional ceramic technology. You can take a metal oxide, charcoal or coal, and aluminum, heat them together, and you get layered ceramics, which will be carbide if you use carbon, or if you do it in nitrogen atmosphere and ammonia, it can be nitride, separated by atomic layers of aluminum, or it can be silica or gallium, are the metals. We call them max phases. My colleague at Drexel, Professor Michel Barzoum, is a leader in this field. So what we did, we chemically etched away a element, because in these max phases, there was strong bonding between a element like aluminum and transition metal like titanium. You cannot purely mechanically separate it, unlike graphite. As a result, we got loose sheets, weakly bonded, that now can be delaminated into two-dimensional flakes. We extensively published on how to make MXenes. So if you want to learn how to produce titanium carbide, for example, we just published in June this article in Nature Protocols. If you don't have access through your library, feel free to write to me. I will always be glad to share copies of our papers. We wrote a review of different synthesis methods recently and many more. We also teach twice a year a course online also, how to make and characterize MXenes. We want everyone in the world learn and be able to use those materials. And of course, there are predictions of many more materials to be made. I won't go into these details. What is important for you to know? That if we start with max phase synthesis, the first method developed, we can etch it in acids. It can be hydrofluoric acid, that's what we started, but it can be a mix of different acids. For example, hydrochloric acid with metal fluoride, sodium fluoride, lithium fluoride. You can do it electrochemically, alkaline, many others. But you also can use emulsion salts, chloride salts mix, or gases, for example, chlorine. You can also do CVD or even transform two-dimensional oxides or chalcogenides or graphene into MXenes. So there are many ways to make it. But depending on how you make it, for example, in aqueous environment, you will always get oxygen hydroxyl group and a halogen, for example, fluorine, if you use fluoride salt. If you use halogen etching, emulsion salt, gaseous, you will end up with a halogen on the surface. So it means different methods will lead to different products. But what is important? All of those synthesis methods are scalable. All of them allow one to produce material in practical quantities. Here is my postdoc, John Wang, holding 1 kilogram of MXene produced in our laboratory, titanium research. And here is my undergraduate student, Marley Downs, holding probably about 8 liters of dispersion of niobium carbide, niobium-2 MXene flakes in water. So what it means that you can make these materials in quantity. So it means that applications are not limited to exotic electronic or optical devices. They can be used in water desalination, energy storage, energy generation, thermal management. As the application, a large amount of materials is needed. Moreover, just a year ago, the first paper appeared in Science from Professor Talapin's group from University of Chicago, reporting on chemical vapor deposition of MXenes. This nice fancy balls consisting of two-dimensional flakes you can see here. And just earlier this year, in January, another very important paper appeared on gas phase synthesis of titanium carbide MXene using a process which is actually very similar to synthesis of titanium dioxide or nanotubes, which are used now in all cell phone, computer batteries everywhere. 3 million tons of titanium were produced in 2023 just in China alone. So in this process, when people start with iron titanate, titanium chloride is formed as intermediate product and used by heating with oxygen at high temperature to make titanium. So it's a white paint on the walls everywhere. This is this titanium. Now, if instead of titanium with oxygen, we add natural gas, methane, at about the same temperature, we can make MXene. So what it means that if you use this process, and you see, for example, here a Ziploc bag full of MXene flakes produced by this gas phase process. If you use this process, the cost of MXene at large volume production should be comparable to titanium or multiple nanotubes when we produce them in the same quantities. So what it means that it's a process that's scalable to very large volumes. Millions tons of MXene is a reality. What this allows us to do potentially, I will show you later. Say, insulate every building, that there will be much better temperature control, minimize the need for air conditioning or heating in winter. There is something else very important. There are some wonderful materials, tellurides, gold, platinum, which are made of rare and expensive elements. However, majority of MXenes being studied contain titanium, carbon, nitrogen. We etch away aluminum or silicon layer. We have on the surface fluorine, oxygen, sulfur, chlorine. So all very abundant elements. And if you use abundant elements, it means it's only economy of scale, making large amounts of materials, and you can make them at low cost and again in large quantities. So again, it's a real technology. So what we do typically in our process, we take ceramic material like titanium, aluminum carbide ceramic, we put it in solution, etch it, make something we call multi-layer MXene or MXene clay, because after aqueous etching, it's very easy after that to disperse it in water. And we get solution of flakes like a paint that you can spray coat on the walls of buildings. And why it's possible without any additives? Because MXenes produced from aqueous environment having oxygen OH on the surface have high negative zeta potential. It means there is negative charge in particles. There is repulsion in solution. You don't need to add surfactant, nothing. Just disperse in water. And you will form MXene paint. It can come in different colors because different MXenes have different optical properties. You saw it on my first slide. Moreover, if you have a solution like that, you can use it, for example, to spray the walls or do inkjet printing. If you concentrate it, you will get a liquid crystalline solution. You can draw fibers, or you can doctor blade and make films by doctor blading. But again, just flakes of MXene in water. And again, making a process is very easy. You take this concentrated solution, and what you do, you spread it, as you will see here on the surface, and let it dry. After that, you can separate this 1 micrometer thin film. You see, it is just 1 micron thin, 10 to 20 times thinner than metal foils people use. You can, of course, make it thicker, 20 microns, 10 microns, like metal foils. But what is important? This, after just drying, this film has strength at least the same or even higher than aluminum foil. For example, you can make current collector for battery 10 times thinner. It's also highly conducting. It's about 10 times more conducting than reducing graphene oxide, where you can, in similar process graphene oxide, dry it, heat it up to 400 degrees C, remove oxygen, and you still will have much lower conductivity and lower strength. But moreover, if we combine graphene oxide with MXene and add some organic molecules to cross-link them, stitch them together, one can get a material, again, very similar. 1 micron, couple of microns thick foil with strength close to 2 gigapascal. This is twice the strength of steel. So we can make materials from solution with strength of aluminum or even higher than strength of steel. But they still conduct ions. You can use them for supercapacitor, battery electrodes, robots, actuators, many other applications. So you see, you can achieve outstanding properties by simply working with flakes in solution. There are many other interesting electronic properties predicted for these materials. I won't go in detail. Two-dimensional magnetism, superconductivity, topological insulators. What I wanted to mention is simply that all these properties are chemically tunable. When we do synthesis of materials, we can select different elements, mix them in necessary proportion. We can modify the surface. We can even intercalate ions or connect by covalent or electrostatic or van der Waals bond organic molecules and tune the properties. Just a very simple example. Work function, ability of materials to emit electrons, very important in, say, optoelectronics, solar batteries, lightning. Change it from 2 to 6 electron volt when we replace hydroxyl groups with oxygen on the surface. And we actually can do it electrochemically. We are applying less than 1 volt potential when we have protons and water between the layers of MXene. And this is possible because the density of the state in these materials is not as high as in copper or gold or other conventional metals. So changing surface termination, we can change it, like in a semiconductor. So basically, those are two-dimensional metals, which are like semiconductors, can have modulation of properties during the work, which opens really new opportunities. And let me give you one example of many where MXene can replace gold, silver, other expensive element. This is example of a Roman cup in British Museum. It is now showing that in reflection, when you look, it will be green. But if you look through the cup in transmission, it will be red because of plasmonic gold nanoparticles. Last year, Nobel Prize in Chemistry was given for exactly this discovery. So one of the scientists who received it, of Russian origin scientist, he received it for discovering plasmonic particles changing as a function of size, color of glass. We can do the same with MXenes. Titanium 2C is red in transmission, green in reflection, but it's just titanium and carbon, common element there. There is no gold. And you can get, of course, variety of other colors. Because depending on structure, composition, we will get different absorption spectrum. Titanium 2C absorbs just the gold at about 550 nanometers. Titanium 3C2 absorbs at 780 nanometers. So it will be actually green in solution instead of red because of this. So I think the idea is here. We have materials where we can control properties, tune properties. But it's great to be able to produce infinite number of new two-dimensional flakes, similar to graphene or molybdenum. It's great to make them in scalable method, kilogram quantities, or eventually tons or millions of tons. It's wonderful that we can use abundant elements like titanium, carbon, nitrogen, oxygen. But is it useful? It would only be useful, and one would only produce millions of tons if these materials had properties that allow us to do something other material can. I already mentioned to you, majority of them are metallic conductors, unlike other 2D materials. But moreover, produced by wet chemical methods, they're hydrophilic. There's like metallic clay. Metal particles you can dissolve, disperse in water, produce from the cheapest, most safe solvent, water. But they're also extremely strong. I've shown you films assembled from these flakes. And they're strong because the flakes are very strong, extremely strong. Those are single flakes of titanium 332 MXene on a silicon wafer. That's optical photograph in optical microscope, not electron microscope. Those are single layer flakes, but you see they're about 20 micron size. I've never seen oxide or chalcogenide flakes from solution of the same size. They will break from vibrations. MXene can survive. Very strong material, but it's flexible, has variety of colors, various optoelectronic properties. You have seen different plasmonic properties, absorption, and it opens many, many opportunities because properties are highly unusual, extreme, and tunable. As a result, there are many, many applications. In my group, we started with energy storage, battery supercapacitors. But if you look lately, sensors have a large fragment. Catalyst, hydrogen evolution, electromagnetic interference shielding. And this all happened over the last 5-6 years only. There was very little research initially after discovery of MXene. You can see how quickly field progresses. And it's actually not slowing down. It's simply at the time when data were collected for this paper, published in January, the data for 2023 were not yet complete. You will see that if you look into any field like sensors, there are many, many different applications. This book, published by my former students recently, summarizes many of these applications, just published this month in July. There are many companies already that produce MXenes around the world. And of course, many more applications are emerging, and you can think what are applications important for you? What are applications important in your country? Is this water desalination? Is this hydrogen production? Is this thermal regulation in houses? Or anything else, and think where you can apply these new materials. And let me give you a couple of examples. For example, depending on composition of MXene, MXenes can either emit heat, infrared radiation very, very well. For example, niobium carbide MXene. Or they can emit very little, keeping all the heat shielded. So they can cover the range from polished metal to insulators, really, materials, emitters. So if you want to have a space heater by electrical Joule current passing Joule heating, you use niobium carbide. If you want, put a coating reflecting, preventing infrared radiation, heat radiation coming through a window, you can use titanium 332 MXene. But there is an important difference. All the metals have conductivity like 100 to 300 watt per meter Kelvin. Titanium carbide MXene film I showed to you, like a micron thick film, has conductivity less than 1 watt meter Kelvin. So if you want to do heat shielding, it will be at least 100 times better than reflective metal foils or coatings in window. You can see Drexel logo, Drexel Dragon, stays cool, blue, after put on a hot plate. And this is like a 200 nanometer film. Carbon will be heated just like an environment. We put it in a 125-degree heated plate. And you can see even after 5 minutes, basically stabilizing the temperature field, it's only 40 degrees. So more than 80-degree temperature drop from 200 nanometer. This film is like 300-400 times thinner than a human hair, and it provides such thermal shielding because absolutely unique, low emissivity and low conductivity. Imagine what impact it can make, replacing thick thermal insulation people use in buildings to keep building warm. They can be used for infrared, also making your clothes, keeping you warm, very thin clothes when it's cold, or replace space blankets with much more efficient films compared to metal on Mylar. So those are properties that open new opportunities. There are many others. Energy storage, this is our review in Science published a few years ago about role of nanomaterials. Again, MXenes are about titanium-32, if you take 100 times more conducting activated charcoal used in the fastest energy storage devices, supercapacitors, electrochemical capacitors. But transition metals, niobium, vanadium, titanium can change oxidation states. They're used in batteries to store more energy by redox reaction. So we want to create fast energy storage devices like batteries that can be charged in seconds. Because of much higher electrical conductivity, you can run high current through it and very good ionic conductivity. And indeed, we showed in aqueous system, we can have charging at 100 volts per second, 10 millisecond redox charging process. And supercapacitor made of MXene, we can run for 500,000 cycles with 92% retention of capacitance. And it's still, as you see, there is a redox process, not just double layer that we can see here only. So these materials open new opportunities in energy storage. But also what is important, we can develop batteries by simply printing them on a wall. Printing micro devices, flexible, wearable devices to power wearable electronics. That someone being very far away from modern hospitals can wear a patch which can collect all the vitals about the health that can be sent through your cell phone to a hospital, to a doctor, or in the future to a supercomputer that will analyze data and send the diagnosis back that a doctor can distribute medicine or maybe even ship medicine to the person. So this is how we see the future of medicine. For this, we need functional textiles. We need flexible, printable, wearable electronic devices, which nanomaterials can afford. Very similar way, it's not only energy storage or printable devices, energy harvesting in many different means. Let me show just one example again. There is a method of harvesting energy discovered less than a decade ago, which is called transpiration-driven electrokinetic power generation. It's a very fancy name, but in fact, it's very simple. You take porous film, you dip it into, for example, seawater, water with salt, conducting, and water evaporate, there is potential development, and current starts flowing in a conducting substrate. People used carbon, but the amount of energy, power was very, very low. When we used MXene, because of its hydrophilicity, high conductivity, high concentration of electrons, we moved in areal and per device power by orders of magnitude. You can see this is logarithmic log-log scale by 2-3 orders of magnitude above everything done before. And now it becomes a practical solution. But again, it's a very simple one. It can be used in the US. It can be used in Africa. It can be used anywhere because it's a very simple way of harvesting energy from salty water, basically. Sodium chloride solution in water. And it can deliver useful energy, voltage, and current. Another big problem around the world nowadays is water purification and desalination. And again, because of these membranes, where we can use applied potential or simply spacing between the layers to sieve ions, one can do separation of ions, removing toxic ions, heavy ions, or desalinate water. Moreover, as you see from this published by not by us analysis of MXene-based membrane for water production, you can see MXene came into the field much later than any other materials. But based on the rate how they grow, they already outperform greatly in number of publications the topic, all other materials but graphene oxide. But from acceleration, you can see that a couple of more years and they will be dominating force in the field. Many other fields, electromagnetic interference shielding, protecting your cell phones, all other electronic devices from interference. MXenes outperform all other known materials, can reflect, can absorb electromagnetic waves. And again, we can need them. We can make antennas which you will wear in your clothes. We can make sensors that will help do sweat sensing. We can take a component 3D printed or injection molded, which is polymer, deep into MXene and make it behaving like a metal, for example, for guiding electromagnetic waves. 100 times cheaper, 10 times lighter. We developed it for satellites of technology, but you can use it for transmission anywhere, including your microwave oven, making very light, inexpensive transmitters or for communications in the country. Many, many other examples can be given. This is light emitting diode, organic OLED, where using MXene instead of ITO allows not only make it flexible because ITO cracks, but also less expensive because it can be processed from aqueous dispersion, and this logarithmic scale 10 times brighter. So luminance will be 10 times brighter compared to the same OLED with ITO. So you see, we can talk not about improvements of 5, 10%, 20%. We're talking about orders of magnitude improvement in properties compared to modern materials like ITO or gold or graphene when we use MXenes. And it goes now everywhere. From the very slow beginning, biomedical application, from cancer treatment to wound healing, to medical diagnostic, wearable electronics, antiviral, antibacterial coatings, very high sensitivity, better than gold. Those are those 3 gold electrodes, commercial and lab produced, and a signal that you can record. You see more intense spikes coming from MXene to, for example, controlled muscle activity in a hand, or encephalography, or any other similar application. People talk about MXene-based electronics like a Maxitronics building roadmaps. So I hope you got an idea. There is now a large family of new materials that can be made in quantities using scalable method from common elements. And there are very attractive electrical, optical, mechanical, electrochemical, chemical properties. Of course, we're still in the beginning of the road. Very small number of, huge number of materials have been produced in this system. We learned how to control the surface chemistry, defects, how to interface them with other materials, bring them into polymer, ceramic, metal matrices, combine them with other two-dimensional flakes like a graphene oxide, clay, boron nitride. And of course, designing with these materials as engineers to find what is the best application, where these materials can make the biggest impact, which of these many MXenes can be used in energy storage or medical diagnostic like breath analysis, or implantable electrodes, or many, many other different applications. There is a journal dedicated already to MXene, graphene 2D materials, which is published by the Graphene Council and MXene Association, Springer Journal. There are many conferences. Next week, we will have a MXene conference at Drexel with more than 200 people on site and many more online. You can still register for online attendance. All the talks will be transmitted. I'm organizing, in addition to this conference, UCAMAT conference in Montenegro. There will be a session again on MXenes. There will be a MXene symposium at the European AMRS meeting in Warsaw in September, and the 5th International Conference on MXene in China in October. So you get the idea. There are many events dedicated to MXene, and you also know I will come to speak to African AMRS in December. And I will be organizing a Gordon conference on nanomaterials and energy technology, where, of course, naturally, you will also see a lot of MXene in California, in the US in February. And this is my very last slide. Science is beautiful, and many of us working with nanomaterials make optical, scanning, atomic force, transmission electron micrographs. And we started with my former student, postdoc Babaka Nasuri, a competition called nanartography. You can just go online, type nanartography, and you come to it here. You can color or submit beautiful black and white image by the end of September. We have prizes up to $1,000. We use these images on our annual calendars. For example, I can show you one you should be able to see on the wall of my office, like this one. They go on covers of journals. For example, I showed you beautiful color of Nature Protocols. This is one of winning images. So you can win prizes up to $1,000 and also become not only rich, but also famous with your pictures being published here. So explore this opportunity, encourage your students to participate and submit images. With this, thank you very much. I will be glad to answer questions, if any.
Thank you, Professor Gogotsi, for this great presentation. If together we can thank him, if some upload. Now we move to questions.
Yes, feel free to either ask or type in the meeting chat.
Yeah, you can raise your hands or put in the chat.
Mm-hmm. I don't see any question at the moment. I assume I was either very clear or
there is Rusin who asking the floor.
Yeah. Okay. I see Rusin. Yeah. Raise a hand. Yeah. Unmute yourself and ask, Rusin.
Okay. Thank you very much for this nice talk, Professor. I am Dr. Rusin Loncho from University of Yaoundé 1, on material chemistry in Cameroon. My question concerns the green aspect of the preparation of MXene, because it has really nice application, and I'm wondering if in terms of environment, because we use a very, I would say, harsh etching agent like fluoric acid, which is normally not very good for the environment. So what is the direction of the research in that way to produce a very environmentally friendly? Thank you very much.
Yeah, thank you. It is a very good question and a very important topic. When materials are just discovered, no one really pays much attention how environmentally friendly they are, how the process can be done cleanly and sustainably. When materials start show real impact and produce larger quantities, it becomes an important issue. And on one hand, you're absolutely right. When we etch it in HF, it requires acid and produces acidic residues that need to be taken care of. It's still much less compared to what chemical industry uses today, and will never use as much. But that's why I talk about other methods. For example, direct synthesis. When we use materials that are used to make currently titanium, we make material where you can basically reuse the same chlorine or other agents. So you don't really spend much except of a mineral like ilmenite and natural gas. At the same time, what is also important, the fate in the environment. What happened? But if you take titanium carbides, titanium carbonitrides, nitrides, when they oxidize, degrade eventually, they form titanium. The same titanium we use everywhere, which is quite environmentally friendly. People look at toxicity. So for majority of materials, this is less an issue. But as we move forward, we need to look for the most environmentally friendly ways to make them. And at the moment, it looks like gas phase synthesis or synthesis from graphite is offering the most sustainable alternative to the current synthesis methods. I see Nutifafa Domon has also a question. Please unmute yourself and ask.
Yeah, thank you very much, Prof. Nutifafa Dumont in Penn State, not far from you, Philadelphia. I'll also be in Kigali in December, so we might probably have a chance to chat. A very interesting presentation. I've heard a lot about MXene, had a friend, Dr. Yury, I think he'll be coming to your conference, who also works in that area.
Yes, Abdullah Yury will be there, yeah.
Exactly. So I work in the space of photovoltaics and optoelectronic devices for various applications. I know MXene found application in this area, especially for solar cell, as you mentioned. My focus is more into the stability and reliability of these devices. I've seen a few papers that have used MXene to kind of prolong the life time of these devices. My question for you, as somebody who has great knowledge, what makes them unique? What are the properties that, because I know they have electronic properties, but what makes them unique in terms of stability in prolonging the lifetime of these devices?
Well, people primarily report on prolonging the lifetime of a perovskites. And MXenes are compatible with halides very much. They're stable in halide environment, so they won't react with iodine or other halogens in halide perovskites. And you can also tune their surface chemistry and work function to match the best way possible increase performance of solar cells. So this is my current understanding why they stabilize solar cells, giving them stable performance, because electron transport layer or hole transport layer used there will be stable, and the interface between the perovskite and MXene will stay. However, people also explore them in cadmium telluride, thin film or quantum dots solar cells, in silicon solar cells, to provide, for example, higher conductivity, have simply solution processed electron transport layer, or very similar to what I showed to you for OLEDs, just making it flexible, producing solar cells that can be flexible, bendable, and even foldable. So I think those are sets of properties. So optical properties, conductivity, and surface chemistry, which is stable in contact with halogens or halides.
Okay, thank you very much. I hope that in the future we can meet and have some exchange with some
looking forward to
as
it.
well. Yeah.
Also, 2 people from my group will be joining the conference along with myself.
Okay.
And
So
definitely, I always look at conference an opportunity to meet people, communicate, establish new collaborations.
Great.
And that will be a great opportunity.
I'll be there with one of my students as well, so we can have a meeting then. Thank you.
Wonderful.
Professor, we have question in the chat. Crowd Pandi.
Okay.
Oh yeah, I can
Nutifa.
see questions now. All right, let me scroll through them quickly. Okay, question is, what is the role of MXene in biocompatible and in vivo continuous glucose monitoring in mice? Look, again, one thing you need to realize, I'm not an expert in everything. I'm a material scientist, material chemist. We usually work with people who develop application, whether it's solar cells or it is a biosensor, glucose sensor. The idea is here usually twofold. One, you can have a material which is electronically conducting, but conductivity of it changes when molecules adsorbed or electrochemical reaction happens. And this is what people use in sensing, particularly glucose sensing and others. So people design sensors based on changing on resistance or electrochemical response from the material. So whether it's a glucose in mice or glucose in people or saliva or blood analysis and sensing here. And MXenes are hydrophilic, unlike carbon materials. And they have this, again, this tunable surface chemistry, which allows you to attach antibodies for some type of a sensing, which allows you to work directly with liquids, and high conductivity allows to do both resistive and electrochemical sensing. Sintering of MXenes. Yes, you can to a certain extent sinter MXenes because there will be cross-linking, I would say, with the material. But you also can sinter them with ceramics, for example, or metals. There are very few publications on this topic. You need to work at moderate temperatures, typically below 800–900 degrees C, at least for extended sintering. Short time exposure can be shorter because at higher temperatures, MXene will transform into conventional cubic carbides or nitride nanoparticles. So this is typically 600 to 1,000 degrees C temperature limit for MXene, depending on the composition. Okay, more questions. I want to synthesize MXene for energy storage applications and water filtration. How to get exact proportion of constituents and mates in film for filtration. Read our papers. We really describe in detail, and we will be teaching a course on site on Sunday this week, but we will again teach online course in February. We describe in this course in 5 days how to make MXene and how to process in film and characterize properties of flakes and films. So this is how you learn. But again, if you need to link to our papers, write to me and I will provide information. Thanks here. Another question, can optical properties be enhanced by heterostructuring with chalcogen 2D, like a chalcogenides? Short answer is yes. People combined moly disulfide, tungsten disulfide with MXenes. Moreover, I didn't talk about it today, but we can also make MXene with chalcogen on the surface. It will look on the surface like a chalcogenide, sulfide, selenide, telluride. But inside, there will be not just a metal, there will be carbide layer. So it's a kind of a hybrid between chalcogenides and carbides nitrides. So it's a matter of designing materials, but one warning. There are so many opportunities. You really need to look into using modeling, simulation to predict properties, not just by trial and error, mixing every possible chalcogenide with every possible MXene, because the number of combinations will be infinite. But they have different optical properties, they may complement each other, and definitely this is something I see a future of assembled materials. A question about strengths. Yes, you have seen how strong these flakes are. You can certainly improve the strength of structural materials if we can assemble a film which is twice the strength of steel. Certainly, it can improve properties of metals. We showed before, together with Professor Talapin, that by adding MXene to light alloys, one can increase strength by 70% without decreasing strain to failure. So material remains ductile, but becomes much stronger and much higher modulus, stiffer. So how do you get the interaction between soluble polysulfide with titanium carbides and has fluoride ion? People use MXenes in metal sulfur, sodium sulfur, lithium sulfur batteries for a couple of reasons. One, it provides conductivity to poorly conducting sulfur or non-conducting. Sulfur is dielectric. But it can also absorb and catalytically break polysulfides. One of my PhD students, Gita Valroso, studies this behavior, and we showed, depending on surface chemistry, you will get different absorption. Titanium 3C2 with fluorine on the surface is not the best. But titanium 2C, niobium 2C do a good job. And depending on surface chemistry, again, by changing surface chemistry, you can improve absorption. So it's all about, again, surface chemistry of MXenes. Another question, MXene have mostly metallic properties. Some example can be tuned into P-type and N-type semiconductors. Yes, there are some examples. There are papers predicting opening the band gap in MXene, but there have been much less work because there are so many two-dimensional semiconducting materials. Honestly, I don't know what MXenes can add to the family of semiconductors. Maybe they can. Maybe this chemically tunable semiconducting behavior. But we have not done anything ourselves in this field. But for example, MXene with different N-type, P-type properties have been explored for sensing, for gas sensing applications. And this is where they seem to show very nice performance because you can record for changes in conductivity, various gases. I hope I answered all the questions.
Thank you very much, Professor.
Hello?
We will stop here. I don't know if it's the last question. Last question, please, the last one.
Yes, it will be the last one. Hello, Professor Yury. It's a pleasure to have this presentation. I asked you a question, but before the whole questions that you have, I'm working on the capacitive deionization. For 1 year, I'm trying to do the MXenes, but unfortunately in Egypt, we can't have too much titanium. That's why, and till now, I'm still insisting to work on the MXenes. But if you have an advice for me for even having that titanium, even if I went to the AMRS or I can afford a little quantity of, what should I do? Should I ask for the max phase and continue after the max phase or what? Because the electrode material is one of the common problems we have in the CDI. So if I can have the max phase or if I can do it in another property or something, what should I do? Yes.
Look, at the moment, there is no really large volume production of MXene. You can buy MXene for Sigma Aldrich, for example. You can buy MXene from the company I mentioned in the beginning. For example, Carbon Ukraine, it was in my very first non-technical slide. Well, Carbon Ukraine, you can go, for example, to this. But it's much less expensive to buy max phase, and also you can then control the synthesis properties here. So we recommend people usually buy max phase and do the etching. And if you look at our paper that I showed, for example, here, we describe the synthesis process in, well, there is a paper, this paper, in very much detail. It's really a protocol. It's step by step. Take this amount of materials, wait, mix solutions, put in this solution, heat it to this temperature, wait for the time, filter, and so on. So if you can follow this protocol, you will 100% certainly get good quality MXene. And I suggest this company because we buy ourselves kilograms of MXene from the MXphase, sorry, from them to make MXene. So this is a material which was used in this paper to do the synthesis. So this is my best advice. However, there are MXphase and MXene suppliers in China, India, Korea, UK, elsewhere. But at the moment, this is the most developed method from MXphase.
Yes. Thank you. Thank you, Professor, so much.
You're welcome. And again, contact Michael Naguib, who is from Egypt, and I know he speaks to Egyptian scientists and media frequently and
He's
visits
a friend
sometimes.
of mine and my professor too. I know Michael so much. He's a very, very interesting one.
He is an excellent scientist.
Please, Professor, people are asking for the slide. If you can share it with Prof. Bululu, that we can have it to give to others.
I will
Possible.
send the PDF version. Yes.
Thank you.
You're welcome. Again, thank you very much for your interest. It was great to see at the peak time about 80 people listening to the talk. Thank you for all questions. And again, I'm always very much open answering questions. If I don't know an answer myself, I will redirect you to my students and postdocs who often are typically know more than me about the subject. So if you go to our website, you will easily find my email. You will find emails of my students and postdocs. You will find topics they work on. So feel free to ask questions, not only on myself, but also other members of my research team. And we want everyone to succeed in exploration of MXenes. Thank you very much. Have a wonderful
Thank you,
day.
Professor.
And I look forward to seeing many of you at the African AMRS meeting.
Thank you, Professor.
Goodbye now.
Goodbye.